Welcome back to another video of Learn with Sriandasla. Today we'll be learning about thermodynamics. It has been said many times that engineering is the industrial application of science. Unfortunately, many engineers get so involved with technology that they often forget the basic principle of science. In the case of liquefaction of gases and cryogenic system, however, the two disciplines are internally associated and it is very difficult to do any worthwhile work involving cryogenic system without a comprehensive understanding of physical branch of science, which is thermodynamics. The basic principle of thermodynamics is the first law or the principle state very clearly that the quantity of energy in the universe is constant. It is a law of conversion of energy. Energy cannot be created nor destroyed during the process, although it may be changed from one form to the another. Indeed, thermodynamics deal with the relationship of various forms of energy. In essence, the first law states that any changes in the internal energy delta U is independent of the path and may be expressed as delta U equal to UF minus UI equal to Q minus W, where WF is the final energy, whereas UI is the initial energy, and W is the work done, and Q is the heat applied, heat expelled. So heat expelled minus work done. Heat expelled minus work done is equal to the final energy minus initial energy. So U equal to internal energy. Due to the motion and configuration of the substance, molecules, atom and particles, and PV, which is external energy due to substance, pressure and specific volume. K is kinetic energy, which is V square by G, where V is the velocity due to the motion of the substance or system, where V is the velocity of G is the gravitational constant, which is 9.8006 meter per second square. Potential energy is Z due to the substance position in space. There are other categories such as magnetic and surface energy, but they could be ignored for the time being, as this text deals only with gases. The external manifestation of energy are heat Q and work W. The term heat is applied to the transfer of internal energy from one substance to our system to another because of the temperature difference. So it's applied. Applied. The term work is applied to the transfer of internal energy to mechanical motion. Neither heat nor work can be considered as internal energy. If the system is as internal energy, neither heat nor work is considered as internal energy. If a system is subjected to a change and the final state is identical in all respect to the initial state, and if only work and or heat has been exchanged between the system and its surrounding, then it can be said that if the system has received heat, then the system has transferred work. If the system has transferred heat, if the system has received heat, then the system has transferred work. If the system has transferred heat, then the system has received work. There is a constant relationship between work and heat. The empirical relationship between work and heat is 1 calorie. 1 calorie equal to 4.168 joule, whereas 1 kilocalorie is equal to 4.186 kilojoules. So 1 calorie energy equal to this number of work done, or what? 1 calorie is the heat required to raise 1 gram of water from 14.5 degree to 15.5 degree. 1 kilocalorie is the heat required to raise this water from this. It must be emphasized that heat Q and work W are not properties of system, but rather the effects of the interaction of the system and its surrounding. When Q is applied, then W work is done, and the difference between them is the internal energy. I think that's what I remember. And final internal energy and initial internal energy is the internal change in internal energy. Oh no, Q minus W is the change in the internal energy. That's what I'm understanding like that, okay? But yeah, you do your math. When the effects of the interaction are balanced, the process is reversible. If they are not balanced, which is more realistic in practice, the process is termed irreversible. Enthalpy. Let's learn about enthalpy, which is also known as H, and it is J by kg, so work done by kilojoule. Okay, let's continue enthalpy. So enthalpy, or the total energy of a system, is the sum of its internal and external energies, or U plus PV, where U is the internal energy and PV is the pressure volume product. Moreover, the expression U plus PV should be considered as an entity and not separately. So in this absence of any work other than that of expansion, any addition of heat to the system manifests itself in an increase in enthalpy. Other than expansion, if heat is added, then enthalpy can be increase. So मैले जब इन्थाल्पी गएर पढ्दाखेरि लाइक इन्थाल्पी चाहिँ एउटा हिटसँगै रिलेट जस्तो पढिरहेको थिएँ है. So in absence of work done other than expansion भन्दा अरू absence भयो भने हामीले चाहिँ इन्थाल्पी भनेको चाहिँ heating भन्ने बुझ्छ के है. So conversely, an extraction of heat results in decrease in enthalpy. Enthalpy, moreover, is a point property. It has no absolute value, and the engineer deals only with the difference in enthalpy between the initial and the final stage of the system. When there is a temperature increase from temperature 1 to temperature 2 at constant pressure, there is an increase in internal and external energies, which can be written as follows: H equal to H2 minus H1 equal to U2 minus U1 plus P2 B2 minus P1 V1 divided by J equal to M Cp T2 minus T1, where M is the molecular weight of the gas and Cp is the specific heat at constant pressure. The above equation is applicable to an ideal gas if the specific heat is a variable and function of the temperature. The change in enthalpy is an integrated quantity H final to initial mCp delta T. The change in the function H or delta H is a measure of any of all heat effects and is the basis of all total heat chart and tables. The latter tables are more widely used for the development of cryogenic processes, systems, and operating procedures. To summarize, the previous paragraphs, works and heat are manifestation of energy in transition. In a heat exchanger, energy is transformed from a warmer system A into a cooler system B. Energy is transition in heat Q. On the other hand, if a gas such as steam expand to drive a piston or turbine, the gassing decreases in enthalpy. Uh, on the other hand, if the gas such as steam expands to drive a piston and turbines, if the gas expand, then the gas decrease in enthalpy. Okay, contraction मा चाहिँ बढ्दो रहेछ. Whereas the machine gains in work. In latter case, the energy transition is called work. The energy in transition is called work. Thank you for watching. See you another video. Bye bye. Take care.